Good day, everyone. How are you all doing? How is everyone doing out there? Okay, come on in, come on in. Um, Welcome to Yebo Tutor live stream help on this beautiful Monday. I hope everyone is good, is having high energy for the week, and is pushing as much as they can as the week is starting right now. Okay, great. Um, if it's your first time, don't forget to subscribe and click the notification button so that whenever we are live, you'll be notified. And also on the description of the video, please do follow us on the social media platforms. Now we are available on Instagram. We're also available in TikTok, as well as Facebook, and also the WhatsApp group is also available. Please do tune in and just click that WhatsApp link. Then you can join the WhatsApp group. Then we can assist each other 24 hours. Hashtag trial exams preparations. So today we'll be doing chemistry. So on chemistry, we'll be looking at the electrolytic and the galvanic cells, which is on paper 2, grade 12. So it's quite great and so fantastical that we meet again, and today we'll be doing electrochemistry, which comprise, or when it's subdivided, it's electrolytic as well as the galvanic cell. Okay, great. So let's get down to the business of the day. As always, let me start with a small overview before we look at questions. So what is important, or what is so crucial for you to understand, is that when we are talking about galvanic electrochemistry, well, we are talking about, let me just write it here. Okay. Okay, great. Sorry about that. So when we are talking about electrochemistry, we are talking about, let me just sort of like do a mind map, which is electrochemistry. So when we are doing, or when we're writing our essays, we always start with a mind map. So the mind map which I had prepared for you guys for electrochemistry is this one. So electrochemistry is comprised, or it's consist of the, as we say, that it has the electrolytic cell, as well as the galvanic cell, Okay, so we put them as well. Put them, because like we are doing our mind map. Here we are. Then we can see that these two, or electrochemistry, is subdivided into two: the electrolytic cell as well as the galvanic cell. So there are different processes which occur in these two different cells. So you must be able to be careful when we are looking at these two cells, because if you look at these two cells, they have differences between the two, but both of them, they're under one subsection which is called electrochemistry. So the difference which I'm including here is that, for instance, on the galvanic cell, we are talking about the relation of current and potential difference to the rate and equilibrium. We are also talking about the movement of ions on the galvanic cell. We are also talking about the electron flow. We are also talking about the salt bridge which we have on a galvanic cell. We also have the cell notation, which we must be able to know. We also have the cell reactions, as well as the EMF of the cell. And we also look at the spontaneousness of the reactions, and we also look at the standard electrode potential. So you can actually see that they are totally different, because that is a galvanic cell. Then on the electrolytic cell, we are looking at more specifically the decomposition of copper chloride. We are also looking at electroplating, e.g. the electroplating of the iron spoon with silver or nickel. Then we are looking also at the refining of copper. We are also looking at the electrolysis of a concentrated solution of sodium chloride and its use in the its chloroalkyl industry. And you also have to look at the recovery of aluminium metal from bauxite. So you can actually see that there are two different things. So for instance, they'll definitely ask you maybe what's the difference between an electrolytic cell as well as a galvanic cell. You must be able to highlight that on the galvanic cell, we have the salt bridge. On the galvanic cell, we are looking more specifically about electron flows. On the galvanic cell, we are looking at the movement of ions from one electrode to another. We are also looking at the relation of the current and also the potential difference to the rate as well, as we are looking at the standard electrode potentials. Great. Also now on the electrolytic cell, now we are now looking at so bear in mind that every time when you're looking at the difference between two cells, always know that you use the table format. There's actually 1 mark for actually be able to distinguish between the two. Always, even in life science, apply that table first. The moment they say determine or distinguish the two, use the table so that you can get 1 mark for just be able to distinguishing them in the form of a table. So now we are saying that we have already spoken about the galvanic cell. Now on the electrolytic cell, the important things which is done under the electrolytic cell is that we are looking at the decomposition of copper chloride and the electroplating. Electroplating is the most important process which is occurring at on the electrolytic cell, because on the electroplating, we are, for instance, e.g., we are looking at the electroplating of an iron spoon with silver or nickel. So those things are so essential. So before we move on to dwell more on these two, what is also important is to understand the different terminology words, or the words which we use when we are looking at these two different cells. So on these two different cells, the first thing, or the important terms or definitions which are so crucial on galvanic as well as electrolytic cell include the following. So for instance, we must be able to know what is a galvanic cell. Yes, we are able to know the characteristics of a galvanic cell. Yes, we already have stated that the difference between the electrolytic cell as well as the galvanic cell. But what is important is now to be able to determine what is a galvanic cell. So the definition of a galvanic cell, of course, make sure that you use the exam guideline, because if you come with your own definition, you're gonna be in trouble, in the sense that the moment you use the and the is, you will be marked partially. So please use the exam guideline definition. And the exam guideline definition say that the galvanic cell, it is a cell which converts the chemical energy into electrical energy. So we are looking at this galvanic cell, and we are saying that it converts the chemical energy to electrical energy. Okay, great. Now this galvanic cell also, it's also known, or is also called the voltaic cell. Okay, those two are all its cell. Why is it called the voltaic? It's because it's self-sustaining. It doesn't need many things. It doesn't need a power supply. It's self-sustaining, and it is self-sustaining electrode reactions. So that's a galvanic cell. So if they ask you what is a galvanic cell, you can define as a cell in which chemical energy is converted into electrical energy. Right. So now we have already defined the galvanic cell. What is an electrolytic cell? Now the electrolytic cell is a cell which converts the electrical. Let me just write this as well. It converts the electrical energy into chemical energy. So we can actually see here that there are actually two. Even they are also different according to their definitions. The galvanic cell converts the chemical energy to electrical energy, whilst the electrolytic cell converts the electrical energy into the chemical energy. So you must be able to know those two definitions. So now we have what we call the oxidation and also the reduction. So what is important is to be able to define these two terms. Okay, so the first thing which they will have to say is that, define oxidation and reduction in terms of the electron transfer. So it can, those two, oxidation reaction and the reduction, can be defined in two different ways. It can be according or in terms of the transfer of electrons, or in terms of the oxidation numbers. So you must be able to know both the definition. So now we are defining. Now we want to define. Now we want to define oxidation and reduction. So we said the first one, we're going to define oxidation and reduction in terms of electron transfer. So what is oxidation in terms of electron transfer? So oxidation in terms of electron transfer is the loss of electrons. Just like that. It's so easy. Oxidation is the loss of electrons. Then we must be able to define also reduction in terms of the electron transfer. Let me underline this part, which is so crucial, that you must know that when they say define the oxidation, or they say define reduction in terms of electron transfer, you must define oxidation as oxidation as the loss of electrons. Now if it's the loss of electrons, what's reduction? Now it is the gain of electrons. So they are just vice versa in each other. It's like the opposite of each other. Okay, now we can also define these two terms in terms of the oxidation numbers. Also do that in terms of the oxidation numbers. So when we do that in terms of the oxidation number, what is important is to understand that oxidation, number one again, oxidation is an increase in oxidation number. Oxidation is an increase in oxidation number. So actually the trick which I can give you is that just know one, then the other one is the reverse of the first one. So if you can just tell yourself that I'm going to know about oxidation, that oxidation in terms of the electron transfer, it is the loss of electrons, already automatically you know what's reduction in terms of the electron transfer. And also at the same time, when we're looking at these two terms in terms of oxidation numbers, you can also be able to highlight the fact that, okay, oxidation is an increase in oxidation number. So what is reduction? Reduction is now the vice versa. So reduction is an decrease in oxidation number. It's a decrease in oxidation number. So those are the things which were so important. But after this, we must also know what is an oxidizing agent. And also, of course, we must know the reducing agent. There's two different terms as well. So if the oxidizing agent as well as the reducing agent. So what is an oxidizing agent? Now we were able to define oxidation. We were also able to define reduction. Now we are looking at the two agents which are so crucial in electrochemistry, which is the oxidizing agent as well as the reducing agent. So what is the oxidizing agent? So this is a substance okay, it is a substance. Let me remove this so that I can create space. It is a substance that is reduced or the one which gains electrons. So you can define it as an oxidation agent. It is a substance that is reduced, or the substance that gains electrons. Which substance gains electrons? It is a substance that gains electrons. So we can actually look at, okay, when we're defining oxidation, we say that reduction is the gain of electrons. So in other words, reduction goes hand in hand with the oxidizing agent. Then what is a reducing agent? So reducing agent now is now the opposite of an oxidizing energy. It is a substance that one was reduced, so this one will be oxidized, or the one which loses electrons, Great. We're just looking at the terminology of the important things which you must know. Then the last two terminology, or the last two terms that I wanted to get relevant with, is what we call an anode. We have an anode. We also have a cathode. So what is an anode? So an anode now is the electrode where oxidation takes place. Okay, so this oxidation takes place on anode, right? So what is a cathode now? And cathode now is an opposite of an anode, which means the electrode, it is the electrode where reduction takes place. Let me highlight some things now. So this is a negative electrode. Then this is a positive electrode. Okay. So we know that when you're looking at a battery, general battery, it has terminals. But in this instance now, when we are talking about this electrochemistry, what is important is that we are using electrodes. Two electrodes. The other one is an anode. The other one is a cathode. The cathode electrode is positive. Then the negative electrode is called anode. So on the negative electrode, that's where there is oxidation. So when we were defining oxidation in terms of the electron transfer, we say that oxidation is a loss of electrons. Now it now makes sense, because oxidation occurs on anode, and anode is where it's a negative electrode. And bear in mind, let me just write this at note well, which is NB, and bear in mind that the flow of electrons in a cell, or in a galvanic cell, in a cell, it's from the anode to the cathode. So now when we say that oxidation in terms of the electron transfer, we say that it's the loss of electrons. Why is it the loss of electrons? Because all the electrons which are on the anode are now being transferred to the cathode, which is positive. So in other words, it will be reduced. That's why it's working hand in hand with the reducing agent. Why? Because it has been oxidized. So now this is so important, that the electrons move from anode to cathode. Now, I want to do one typical example. Just write a galvanic cell. I draw a typical galvanic cell, which can assist us in the process. So maybe let's say that we are having our two different beakers. We have another one here. And when we were distinguishing between the two, we say that they are connected with what we call a salt bridge. This is our salt bridge. Okay, my drawing is not that good, but yep, we're getting there. Then this is a galvanic cell, so we are looking at the zinc, copper cell, so that we can illustrate what we are talking about when we are looking at the galvanic cell. Great, let me use a different color here. So now this is a salt bridge. It's already connecting two beakers. Okay, so what is also important now is to understand that I put this so close. Let me see. We say that in a galvanic cell there are two electrodes, the one which is an anode as well as the cathode. So the cathode is positive, the anode is negative. So let's draw our two electrons. So when we are drawing our two electrodes, just do this. Then we also have another one which is a cathode. Okay, great. Then what is also important, we know that we have aqueous inside. This is so interesting. This section is so interesting. Okay. Great. So these two are the ones which are in red. They are our electrodes. Then these electrodes now are connected to what we call a voltmeter. It's not connected to a power source. It's connected to the voltmeter. Okay. There is our voltmeter. Then now let's label what we have here. So maybe we can say this. We are saying we are looking at the zinc and copper galvanic cell. So this is gonna be our positive cathode. Okay, which is, so let me just write here, this is our cathode and this is the in solid. This is our copper electrode, which is always in solid, which is in solid in this instance. Then this is our anode, which is now having the zinc, which is also in the solid state. Great. Then we have our salt bridge here. On the salt bridge, we say that our salt bridge is having what we call, in this instance, let's say they are having a salt bridge. This is potassium nitrate. Okay, that will be our salt bridge, which is in aqueous. Okay, great. Then now, what is important is to understand that we have what we call an electrolyte. I didn't define that, I forget. So as you can see that there are these small dots which I'm putting inside here. I'm just trying to illustrate that we have an aqueous. So in this instance, since it's a galvanic cell, we are having what we call the electrolyte. Okay, so what is an electrolyte? It is a substance of which the aqueous solution contains ions. Okay, it is a substance of which the aqueous solution contains the ions. Okay, so these dots here acting as ions. So we are saying that this aqueous solution, which is what we call the electrolyte. So we are saying that the definition is the electrolyte. Why? Because an electrolyte, it is a substance of which the aqueous solution contains the ion. So as you can see that we don't have sort of like the solution only, or we can say that the solution which we are having in our two different beakers is called the electrolyte. Then after that, maybe we can say that now. So we know that on the electrode, on the anode, we say that oxidation takes place. So what is oxidation? It is the loss in the 2 plus 2 e. Just write it down. I'm writing now the half reaction on the electrode. So what is important is just to know which electrode is having what. For instance, now we know that on our galvanic cell, the anode is having the zinc. So since the zinc is on the anode, which means that is going under oxidation. So when we're writing the half reaction of zinc, it's gonna be Zn, which is in the solid state. We can just say Zn plus which produces Zn 2 plus K plus 2e minus, which is 2 electrons. This is, I'm going to show you now where we find these half reactions. I'm going to show you now we have what we call the table 4b. Then on the cathode we are having copper. So now it's going to be copper plus copper 2 plus 2 electrons. Then it produces on the copper, which is pure copper. This is going under reduction. This is going under what? Oxidation. So I was just trying to give you like a typical galvanic cell, which you'll be able to know or able to relate with. So you must know which substance is on the anode, which one is on the anode cathode. The moment you know which one is on the anode or which one is on the cathode, we know when we were defining, when we say that the anode is where oxidation is taking place. So that's where the oxidation is taking place. So what do? We go to our table 4. So now let me show you the table 4 which I am talking about. So now let's look at table 4. Sorry. So here we have our table 4. Here is the table 4. So the table 4b is always given at the end of the question paper. Great. This is 4a. I don't usually say use 4a because 4a to need you to be able to, you see, where is 4a? It's now having increasing strength, of which on 4b we are only looking at the increasing strength, and we are now looking at the reducing reagents, and also it have the standard reduction potentials, which is E naught, which is EMF. Great. So this is our table 4b. So as you can see on this side, as you are going down, it's increasing strength of oxidizing energy. Then on the other side, on the left, it's increasing increasing strength of oxidizing energy agents. Sorry. Then on the right, it's increasing strength of reducing agents. So that is so important now. Now let's look what we have here. You can see that we are having all these reactions, half reactions. We have the lithium, we have for potassium, we have for aluminium, we have for chromium, we have for Cr3, we have for iron, we have for Cd, all these things. Then this is a constant, which is, that's why it's 0 actually. It's a constant. Hydrogen is constant. Great. Now let's look at zinc. Where is zinc? Zinc, it's Zn. Where is zinc? It's supposed to be up there. Here it's zinc. So since it's going for oxidation, we still remember when we were looking, we say that oxidation goes or work hand in hand with the reducing agent. Why? Because it's oxidized and it loses electrons. So how do you lose electrons? We can actually see that this will be our zinc here. So this is so important. This is so crucial that you be able to manipulate and be able to use your half reaction table 4b. So I was just wanted to show you that we are getting this Z2N, which is here, and now we can look at that, increasing the strength of reducing agents, and we say that the oxidation and reducing agents, they work hand in hand. So you'll be able to find your oxidation notation or oxidation half reactions. Great. Now let's move forward from that part. I just wanted to show you this part only. Let's go back to where we were, which is here, question 8. Great. Now, okay, let's just put another NP here so that you also remember what I was talking about. So what we are saying right now is we say that oxidation, it has what we call the reducing agent, which goes to being oxidized and it loses electrons. So now reduction now is now the opposite of the above. Reduction will now be the oxidizing agent, which is being, they say, oxidized here. So what is it gonna be? It's going to be reduced. Okay, it's gonna be reduced. Reduced. Then it goes and it gains electrons. Okay, then it gains electrons. So they will ask you, maybe for instance, the functions of a salt bridge. Definitely must know that a salt bridge, it is there because it completes the circuits, you know, those small things which you must be able to realize as well. So what also I want to highlight on this part is to understand that we have what we call the net cell reactions. So on the net cell reactions, what is important is to be able to understand that you have to balance the two. So let me just write it down. The net cell reaction. Okay, net cell reaction. So looking on the galvanic cell which we had above, so looking at that one, we had the oxidation half reaction. HF is half reaction, which was for zinc, which we say that it's Zn in solid. Then it produces Zn2 plus 2E minus. Great. Then we also have the reduction half, which is for copper, Cu2 plus, which is in plus 2 electrons, which gives us pure Cu. Great, which is in salt. So when they ask for the net cell reaction, we look at the oxidation half reaction. We also look at the reduction half reaction. So now we must balance and we see the number of electrons are equal. So we can actually see that 2E and 2E here, which means our number of electrons, they are both equivalent to each other. You can see here 2 electrons, 2 electrons. So since the number of electrons, they are equal, which means that these two are the same. They have the same number of electrons. So now what does that mean? That totally means that these two are okay. So if maybe, for instance, I'm saying that you're giving 1 E here, which means you're going to multiply here by 1, you're going to multiply by 2, so that the number of electrons in both two half reactions can be equal to each other. Okay, so that they can cancel each other. So now we can actually see that if you look at that now, this 2E which we had here, we will cancel with this 2E. So we can actually see the number of electrons, they are equal in both reactions. Then what do we do? How do we write our net cell notation or net cell reaction? So the net cell reaction will be, so we say that we are starting from the oxidation, so it will be Zn in solid plus Cu2 plus. Okay, then we put our arrow. We know C2U is in aqueous, and also this one is also in aqueous. So now we go to the other side again. So we're gonna start with Zn2 plus, which is in aqueous. Then we add Cu, which is in solid. So this is so important to understand the net cell reaction. Great. Now, the last thing which I want to highlight on this galvanic cell before we move to another thing is to understand that the flow of electron current. So electron always flow from the anode through the external circuit to the cathode. As I said that the flow of electrons or the electron current flows from the anode through the external circuit to the cathode. And also what is so important also is to understand the cell notation as well, as we are still here. This was the net cell reaction. Now we want to look at cell notation. So it's not always the case that they give you using these arrows. Sometimes they will use just a a push forward, or the backward two slash, or forward slash, sorry, forward slash, or the backward for slash. So now, what is the cell notation? How do we write? So what do we always do when we're writing on the cell note? Let me write this down, which is so important. We always start from the anode. Okay, we always start from the anode on the left. Okay, then number two, what is important, we use a forward slash. Okay, this is so crucial. We use a forward slash. When do we use a forward slash? We use a forward slash to separate the anode or cathode. Okay, separate the anode or the cathode from its electrolyte. What did you say again about the electrolyte? What is the electrolyte? We say that the electrolyte is that solution which we find in our two beakers. When I was looking at that example here, that is the electrolyte. So we're saying that we use a forward slash to separate the anode to its cathode. Okay, then the last one is that we use these two symbols, which is to representing the salt bridge. Okay, representing the salt bridge. So these two forward slashes, they are representing the salt bridge. Now, great. So for instance, from the example which we had here, which we have here, so we could write this in cell notation, because they will definitely ask you in cell notation. So we say that we use a forward slash to separate between an anode and a cathode. Zinc was on an anode, and Cu2 plus was on our cathode. So we separate them by our forward slash. Okay. Then now we put this arrow was representing it was representing the, sorry, let me just do this. It's not like this. So forward slash, then we put also Zn 2 plus, which is in aqueous. That was our left side. Then now we put our salt bridge here. Okay, then our salt bridge will be for Cu 2 plus in aqueous, then also plus, sorry, we don't put a plus, we put another forward slash for our Cu, which is in solid. So that's how we use the cell notation. Cell notation is so important for you to understand. They won't be using arrows, they will be using the forward slash. One forward slash is to separate the anode from its cathode. Okay, then we use two forward slashes as a salt bridge. All right, so that's what we had for our what do we call this, our galvanic cell. And what is also important is to understand that, just to recap on the galvanic cell quite a lot, but what is important is to understand that oxidation works hand in hand with the reducing agent, and the reduction works hand in hand with the oxidation agent. Great. Now we are now moving forward to almost our last section, or our last part on the galvanic cell, which we call the EMF. How do we calculate the EMF? Okay, so how do we calculate? Oh, sorry, we must look at first the standard hydrogen electrode. So how do we look at the standard electrode, hydrogen electrode? So what is important is to understand that it consists of a glass tube through which hydrogen gas is bubbled over through the platinum electrode, so that the hydrogen becomes absorbed on the surface of the platinum to enable it to react with its solution. So the platinum also carries the current into the solution. So the inert electrode, what is important is to know what is the inert electrode on this standard. It is platinum. Okay, so they usually love to ask, this is always 1 mark, you know. So just to know your net electron, which is PT, like that, which is called the platinum. Okay, great. And also what we know is that the half cell potential of hydrogen, as I was showing you, that we say that it's the 000V. Why? Because we say that it's the standard hydrogen. And what is also important, as we always know, that what is the temperature at room temperature? Temperature is going to be equal to 298 Kelvin, which is like 25 degrees Celsius. That's the room temperature. Then what is the concentration? The concentration, which is illustrated by C, is like 1 mole decimeter cubed. Then also you must know the pressure at standard hydrogen electrode, which is like 101.3 kilopascals. Okay, these are just standards, which are also, I believe, they are at the back of your question paper at the end. Okay, now how do we finalize this? We finalize this by calculating the EMF of an electrochemical cell. Okay, we are now finalizing this by looking at the EMF of an electrochemical cell. So how do you calculate that? It's E naught cell is equal to E naught cathode minus E naught anode. So this is what we use, because we remember that on a galvanic cell is connected to a voltmeter. Okay, a galvanic cell is connected to a voltmeter. So since it's connected to the voltmeter, we must be able to calculate the EMF of an electrochemical cell. And how do we calculate this? We calculate it by using this formula. E cell naught is equal to E naught cathode minus E naught anode. All right, then we'll be able to calculate. So this is so important. Where do we get this E naught and E cathode? Let me show you right now on our table, which I showed you earlier again. So we can actually see where is everything coming from. So we said we are going to use table 4b. So you can see that on the table 4b, we have the segment or the section for half reactions. Then on the right side, we have for E naught, okay, which is always in volts here. So we have E naught, which is always in volts. That is important. That's what we use to calculate the EMF of a cell. All right. Then the last part now, before we do an example. Now let's look. We were looking at the galvanic cell. Now let's look at the electrolytic cell. Right. Now let's look at the electrolytic cell. So on the electrolytic cell, guys, this is the last section of an electrochemistry, which is so essential as well. So what is important about the electrolytic cell is what I've already highlighted, that an electrolytic cell, it's a cell which converts the electrical energy into chemical energy. Okay, so now let's just draw maybe one example for this electrolytic cell. Okay, electrolytic cell, electrolytic cell. It's a cell which converts the electrical energy into the chemical energy. Okay, so the difference now is that we say that on a galvanic it's connected to two beakers using the salt bridge, of which in an electrolytic cell they don't have a salt bridge. The anode and the cathode are in one, and now this one is connected to a power supply. Okay, let's do this. Right, so this is gonna be our cathode. This is our anode. But now on electrolytic cells, there is so crucial information which we must get hold, or which we must know, that on the anode of an electrolytic cell, this time is no longer negative. It was negative on a galvanic cell, but this time the anode is going to be positive and the cathode will be negative. So just the small things which I wanted to highlight, that in an electrolytic cell, the galvanic cell, it is the one which has a lot of work, but the electrolytic cell is just small and precise. The electrolytic cell, it is connected to a power source, which is a battery. Okay, so this battery, now we know a battery contains two terminals, the positive and the negative. So now we are having our electrodes, which are inside the electrolyte in the beaker, which I have illustrated right now. Then on the anode, now it's no longer negative, it's now positive. Then on the cathode is now the inverse, it's now negative. Sorry, it's now the negative side. Now we now know this is just like a small typical example. So this is showing our battery, so close to each other, but here just use a different pen. So this is our battery, then this is our anode, this is our cathode. So now what is important is to understand that the electrodes made from unreactive substance, for instance, they are made from platinum or graphite. So those two, the inert, they are so important. Okay, now the other thing which is important is that the negative ions, which are called anions, they move to the anode where they are oxidized. Okay, so in this electrolytic cell, what is important, what is crucial, is to understand that the negative ions, they move to the anode where they are oxidized. Then the positive ions, which are cations, they move to the cathode where they are reduced. Okay, so the positive will be moving to the, let me just say we have a positive, we have negative. So the negative will be moving to the anode to be oxidized, then the positive will be moving to the cathode to be reduced. And now what is important also is also to be able to use your reduction table the same way we are doing, but now it's now the inverse. What was on the top, we started what is at the bottom now. So just like that, we'll be able to solve the problem. So as I highlighted the fact earlier, that we have few things which are so crucial, that we have the applications of the electrolytic cell. So we can apply the electrolytic cell when we are maybe purifying copper. We are looking at those things. We know that our electrodes now will be acting like impure copper. They will be acting like our impure electrodes, so that they can be able to assist us in the when we are in purifying copper. We can also use the electrolytic cell when we are in the production of chloride gas. Then we also, when we are refining the aluminium. I'll attach a small PDF which I created in the WhatsApp group, so that you can also have this document, because I have put it like some small cells which are actually explaining what I'm talking about. So I'm going to attach it in the group as well. Don't worry. So please be able to answer this. It's like 20 marks in your chemistry paper 2. So what is so important is to understand these two different cells under electrochemistry. So that is what I had for you guys for today. Now let's look at a typical exam question. Let's look at an exam question. So here we are. This is our exam question. All right, let's go. So on the exam question, let's look. It's question 8. All right. So now we are looking at question 8. So the table below shows two half cells, A and B, used to assemble an electrochemical cell under standard conditions. Wow, under standard conditions. Just remember, when we're talking about standard conditions, we say that the EMF of hydrogen under standard condition is equivalent to 0. We also say that the pressure under standard conditions is 101,35 kPa, which is kilopascals. Okay, then also we must know that we have an inert electrode, which is platinum. All right, so now we are just analyzing our question. We're not too hard on ourselves. We are just analyzing what we are seeing on the question which they're given us. So now the first question, they say that state the energy conversion that takes place in this cell. What is the energy? So by the looks of what we are seeing right now, we are seeing the half cell of A, which is C2 plus aqueous plus then 1 one forward slash, which is going to calcium, which copper, which is in solid state. Then now state the energy conversion which is happening. First, which cell is this? Definitely this is not an electrolytic cell. Okay, this is a galvanic cell. Why is it a galvanic cell? We can actually see that we have two half cells there, and we can actually see these two are connected together by the salt bridge. So we know that on the electrolytic cell is not connected to the salt bridge, whilst a galvanic cell is connected to a salt bridge. So our answer on 8.1, our answer on 8.1 now, the conversion, since we know that it's a galvanic cell, so this means that, okay, yeah, that's what I wanted. So what does that mean? Which means chemical energy is converted to electrical energy. Okay, simple as that. So what is important is to be able to just know which cell is the one which we are looking at. Then now let's go to number 8.2. Great. Calculate the mass of silver nitrate AgNO3 used to prepare 150 electrolyte solution. Oh, okay. Used to prepare 150 centimeter cubed of the electrolyte solution in the cell B. This is our cell B, which is Ag, which is silver. Okay, so now we must calculate the mass of silver nitrate. So what do we know about silver nitrate? We know that in our question paper, at the end we have the formulas for electrochemistry. Okay, and also generally on how to calculate this stuff. Okay, great. So now let's calculate together. We want to calculate the mass. Okay, we want to calculate the mass. So how can we calculate the mass here? So we can use any formula. So we know that C is equal to the mass over the molar mass times V. Okay, so what are we given here? What are we given here? We know something. You see, this is so easy, guys. I hope you'll be able to see this. So we want to calculate the mass of silver nitrate. What is M? M is the molar mass. Okay, it's the molar mass of AgNO3. We were taught this in grade 8. Well, grade 10. Then what is the volume? The volume, we were given the volume to be 150. We're given the volume to be 150 centimeter cubed. Okay. Okay, yeah, just to confirm that. Okay, sorry about that. It was just a small glitch. Okay, so we're given 150 centimeter cubed. Now, that's our volume. Let me just use a different pen so that it can have a small effect. So the volume we were given to be 150 centimeter cubed. Then we want to calculate the mass. We know that the mass will be equal to C times mv. Okay, what is C? C is the concentration, and we say that the concentration of the electrolyte, we were told that it's 1 mole per decimeter cubed. Okay, so now what is the molar mass of AgNO3? That's the easiest thing now which we are just doing now. So the molar mass of AgNO3 will be equal to the molar mass of Ag, which is silver. On your periodic table, you find the molar mass, and the molar mass, it's 108. It's 108. Then we add for nitrogen, it's 14. Then we add for oxygen, it's 16, but there are 3 of them, so we multiply by 3. Then we use our calculator. Okay, Then we use our calculator. 16 times 3, it's a 16, 32, 48. 48 plus 14 plus 108, then you get 170 grams per mole. Okay. So definitely now we can be able to calculate. Now we are given this in centimeter cube. Now we must convert it into decimeter cubed. We just divide by 1000. So it's going to be 0.15 decimeter cubed. Great. Now we can actually calculate our answer first. All right. So now we can calculate our answer first. So our answer here, what is going to be our answer? So it's going to be mass is equal to, we said mass is equal to what? We just cross multiply here. It's going to be the concentration multiplied by the molar mass multiplied by the volume. What's the concentration? The concentration is 1. The molar mass is 170. The volume is 0.15. Then we use our calculator. We use our comparators. Let me use mine as well. Then I got 25.50 grams. That is my mass. So it was so easy. The question was asking, calculate the mass of the silver nitrate. Now we know that on the formulas which we have, we know that C is equal to small letter m, which is for the mass, divided by the molar mass multiplied by the volume. Okay, then you can be able to get your true answer. Can be able to get your true answer. Now done with that question. Now on the next question. Now question says calculate question says calculate define the term reducing agent. You see, everything I gave you is cream. It's something which you need as it is, so don't worry about many stuff. Now you just have to define your reducing agent. What's a reducing agent, guys? We have already spoken about this. Can someone just type something on the comment section? What is a reducing agent? What is a reducing agent? What is our reducing agent? What is our reducing agent? What is a reducing agent? I'm looking at the comment section. Can someone grace us with the answer, please? What's a reducing agent? Okay. What's a reducing agent? Come on, guys. Can someone say something? Okay, we have already highlighted that. What is a reducing agent? Okay, let me define it for you guys. So the reducing agent, it is a substance that is oxidized. Okay, so a reducing agent, which is 8.3, it is a substance that is oxidized. Okay, so someone can say that it's a substance whose oxidation number increases, because we say that a reducing agent works hand in hand with the reduction, with the oxidation. Okay, then the next question now. Next question says that 8.4. Write down the name or the formula of the reducing agent. What is the name of the reducing agent? When we're talking about the reducing agent, we say that it's the substance that is oxidized. So what is the reducing agent? Well, apparently, according to what we are seeing here, where it's called copper. Copper is our reducing agent. So someone can just say Cu is our reducing agent. What is a reducing agent? It's an substance that is oxidized, or you can say that it's the substance that loses electrons. So we still remember when we were writing or when we were having our things, or when we were drawing an overview on galvanic cells, we had an anode and a cathode, and we say that this one is the reducing agent where oxidation occurs. So we can actually see that we are given half cell, which means this one is on the left, this one is the other one is on the right. Okay, so the one on the left, which is on the anode, which is gonna be our place for oxidation. So the answer is simply copper. Our answer is simply copper. Then now looking at 8.4.2, looking at 8.4.2, balance the equation of the reaction that takes place. Let's balance the equation, guys. This is interesting. Let's balance the equation. Let's balance the equation. So when we are balancing our equation now, let's balance the equation. So in other words, they need the net half reaction which is occurring that side. So when we balance, our answer is going to be Cu for copper, which is in sulfate, plus 2Ag, plus, which is in our aqueous solution. Then we have our copper 2 plus, right, in aqueous solution, then plus 2Ag in the solid state. That's gonna be our answer. Okay, so now someone is asking me, how did you get that? I'm hearing someone asking me, how did you get that, Fuyani? So let me show you from our table 4b. All right, let me show you now from our table 4b what I'm talking about. So what I was saying initially when I was telling you that we must be able to balance the actual ones, the cell notation. All right, so now let me show you what I'm talking about. So when we come here, so we are having our copper and our Ag, which is silver. Use a different pen. This is our balanced equation, guys. This is our balanced equation. But now let's look, where is copper? Copper, which has 2 positive, gonna be 2 electrons. So here is our copper. We can see it here. So it's gonna be Cu 2 plus 2 electrons minus, then it's giving us copper. Then so when we're writing this as a one going oxidation is going to be Cu in S. Okay, then Cu 2 plus 2 electrons. Why is it written in this? Because it is losing electrons. Now let's look at silver. Where is silver? Can someone tell me where is silver? Silver, it's Ag, guys. So here is Ag for silver. So it's gonna be Ag plus 1 electron. Then it's Ag in the solid. Okay, great. So guys, I want to show you what I was saying, that what is important is to be able to balance. Now we have already written our 2 as an oxidation and as a reduction. All right, so this is our 2 now. Let me just remove this one, because this one I copied as it is on the 4b. Then after that I wrote it since it's going under oxidation. Then now here we are, guys. So let's balance together so that I can do step by step for everyone. So when you're doing step by step for everyone, we can actually see that we say that this is our reducing agent, this is our oxidation agent. Okay, so now we want the net cell. Okay, or this net cell is gonna be what? Now we have 2 electrons and we have 1 electron, so we must balance those electrons which are not balanced. So what is important is we must be able to balance those electrons which are not balanced. So how do we balance that? Since it's 1, it's 2, so we multiply by 1 here, we multiply by 2 here. So when we multiply, it's gonna be Cu in solid, then copper 2 plus 2e electrons. Then now it's now 2Ag plus, which is in aqueous, of course, then plus now 2 electrons, then we have 2 Ag in solid. So now this is now nice. This and this will cancel each other. Then that's when now we are ending. That's why we are ending up with having Cu in solid plus 2 Ag positive, which is in aqueous. Then we have our answer, which we have already written there, that we're gonna have now our copper 2 plus, which is in aqueous, plus 2 Ag, which is in solid. Just like that, boom, that's how you write your equation. Okay, that's how you write your equation. Now let's look at the last question of the day. Actually, that's great. Let's look at the last question of the day. Now, what is the last question asking? What does it want? Next time when we meet, we're gonna do the one for the below, which we have, but I'm gonna see which way we can go. Now, calculate the EMF of this cell. EMF is easy. We know how to calculate the EMF of this cell. How do we calculate the EMF of this cell? We say that E naught cell is equal to E naught of the anode or others will say for the cathode. So it depends on which one. Others will say for reduction. Sorry, so it's supposed to be cathode here. Sorry for that. Minus E naught of the anode. So we know that copper is anode and Ag is cathode. Now we also go back to our table 4b. Let's go together so that we can able to see together. So we say that since from here we say that oxidation is taking place on Ag, which means that's where is occurring the oxidizing reagent, it's on Ag, and the reducing agent is on copper, which means copper is going under oxidation, then Ag is going under reduction. Okay, so now when we are calculating the E naught cell, now we are now looking at E cathode. E naught cathode is the one which is going through reduction. Okay, so which one? We said the one going through reduction is Ag. So where is Ag? Ag is here, which is positive 0.8. So it's going to be equal to 0.8 minus what is cathode. What is cathode? Here is our cathode, which is positive 0.34. Then we subtract the 0.8 minus 0.34. Then that will be 0.46 volts. Just like that. So what were we using? We were using our table 4 to be able to determine the E naught cell. We were just using our table 4. You can actually see this is the formula for calculating as well. E naught cell is equal to E naught cathode minus E naught anode. Then you get your answer. Now, then you get your answer. So sorry. So we were using this formula. E naught cell is got E naught cathode minus E naught anode. Then after that, we figured that the one which was going through reduction is the cathode, which in this case we say that it's silver, and it has the E cell or the EMF, which is 0.8. Then we subtract for the one for copper, which is 0.34. Then we get our 0.46. Now let's look at the last question, or 8.6, right? How will the EMF of the cell be affected of the concentration, okay, of the copper ions in a half cell A? If the concentration of the copper ions in the half cell A increases, how will the EMF be affected? So that's easy. We have already spoken about that. We say that if the concentration of the electrolyte increases, the EMF will decrease. That's why it's actually 1 mark. Okay, so it's actually going to decrease. Okay, it's going to decrease. Then we have the answer that's then let's just do these first 3 questions. Define an electrolyte. We have already defined an electrolyte, and we say that it is a substance which we find there inside our solution. So what is an electrolyte? We say that it is a substance of which the aqueous solution contains ions, right? Then now, is the pure chromium metal anode or the cathode of the cell? Give a reason for your answer. Give a reason for your answer. 9.2. why is chromium metal anode, or is it cathode? So we can actually see that on 9.2. We can actually see that our anode, our chromium metal is going to be anode. You can see that it's anode. The answer is going to be anode. I hear you, don't worry. I hear someone asking why. So now we are now stating our reason why we are saying it's anode. It is substance, it's anode because chromium is oxidized, okay? Because we can see that chromium is oxidized, which means it's going under reduction. Okay, or we can say that oxidation takes place on the anode, or sorry, not anode, sorry, not reduction. Or we can say that it's anode because we can actually say that our chromium is oxidized, meaning that oxidation is taking place at the anode. Okay. Great. Then let me just do this last question, please. Write down the half reaction that takes place on the ring. How will we write the right half reaction that takes place on the ring? Of course, we're talking about chromium. So you can just go to your table again, and on your table 4B, you'll be able to see that's going to be our Cr3 plus. Where is it? Yeah, for chromium, so it's going to be Cr3 plus, which is in aqueous state, plus our 3 electrons, which gives Cr, which is chromium, which is in the solid state. So those are the questions which I wanted us to highlight. Those questions, question 8 and question 9, they're able to cover both galvanic cell as well as the electrolytic cell. I hope I was able to manage to answer your questions. Many people are asking about these topics, so I hope I've answered everyone's questions. And I hope if you have more questions, do comment so that we know where we can assist you. Till we meet again, have a blessed day, and I wish you all the best as you are preparing for your trial exams. Continue preparing, and if you have any question, do ask us questions. We are here for questions so that we can assist you and we can move forward and we can change the world. That's Fuyani signing out. Have a blessed day ahead.